All right. So I'm going to take things in a particular order, just because the last few months I've been thinking a lot about this. So I just want to remind everyone. So when we ended last time, I mentioned that there was this connection between reversibility and rho and quantum mechanics. And I'll get to that all in good time. But there are kind of two different ways to think about the relationship between quantum mechanics and rho. And I realized that I've been thinking a lot about this this particular encoding, and I realized that there was something I had missed before. And the more I've thought about it, the more I have understood some of the technical issues when it comes to this particular kind of encoding. So I just want to remind everyone how the math works. So obviously, names inherit all the algebra processes. So in particular, we can define things like the parallel composition of names, right? That's just the parallel composition of the processes they quote and then take the name of that. And this extends to, complex operations, right? Because, this is well defined on processes, the square root. So I've given a definition of the square root. And so we can define the square root of a name to be just the name of the square root of the process that it quotes, right? So that's kind of the point of these two equations here. So there's also a multiplication of names to processes, right? So if I want to multiply a name times a process, well, I take all the free names that are in Q, and I substitute for them the parallel composition of the free name with that particular name, right? So if X is a free name in Q, then for X, I'm going to substitute X par at P. So let me stop here and just check and see if there are any questions about what I've just said. Does this all make sense?
With the last multiplication is something like a substitution with all free names.
Mm-hmm. It's a simultaneous substitution of all the free names.
Okay.
So basically, you're just taking a name like this and turning it into a name like this.
Mm-hmm.
Okay. And obviously, the definitions have nice properties, right? So the quote of the zero process is an identity, right? And it's also an identity as a scalar multiplier. So we're just going to use star, the normal multiplication, polymorphically for all of the different ways that we sort of think about it as a multiplication. So hopefully that's clear, right? So, and we're justified in this because there's an identity, it's associative, and it turns out also to be commutative, right? So, so like P at P star at Q is the same as at Q star at P, and it inherits that because, you can, to prove that, right, you'd flip it here, right? And then you could unwind it here, so it would be at Q par at P, and then that would be at Q times at P, right? So the properties that we have of the processes extend smoothly in this way, and so this gets, we have the right to think of this as a multiplication.
Okay, can I just ask you, are you defining the multiplication on the left side is multiplication, but not on the right?
This is just notation, right? All we're saying is that, right here, because there isn't an operator like a par of a name in a process, that doesn't exist. So here we introduce the star notation, right? Because we can think of it as a kind of multiplication. But here at this level, right, we don't really have a star, but we're going to say that the star is the par, so that we can use the star polymorphically. Whether we're multiplying names against names or names against processes, we'll use the same notation and we can interpret it polymorphically, right? Does that make sense?
Okay. Yes, thanks.
Sure. Okay. So then it turns out that you can think about contexts, single hold contexts, as it also gives you a notion that's sort of natural in the sense that it's dual to processes. So what I'm really doing here is I'm following these analogies, right? So I'm thinking of names as scalars, processes as vectors, and contexts as one forms or duals to vectors. And so what we'd like to do is to define a kind of inner product, right? So if this is a dual, right, then I should be able to define a kind of inner product. And so what this should result in is a scalar, right? So it should result in a name. So to do that, what we do is we apply k to p, but so that means we're going to put p in the single hole that k has. And then we're going to apply a substitution. And the substitution is going to apply over the free names of k and the free names of p. And we're just going to do this multiplication where w is going to be the name of p par k of 0. So hopefully this all makes sense. Right, it should be very clear. A W is just a name we can form. We know that none of the free names of P can be equal to W. So W will not collide with any of the free names of P. And also none of the free names of K can be equal to W. Again, this is by construction. And so when we do these substitutions, we will get distinct processes, but they'll have the same shape. So it'll be very similar to K applied to P, but it'll be moved over a little bit. So this thing wouldn't ever interact with K or P. And there's an obvious relationship between P's and K's, right? So I can define the perpendicular of T, the transpose of T, to be P par whole. So then this gives us, and if we just fill in the equations, right? Just follow the equations. We'll see that there's sort of the right kind of duality between processes and one-hold contexts. So far everything is looking great. So we can kind of extend this now to quantum mechanics in the natural way, right? This is exactly this sort of definitions that we would want, and it preserves, these definitions preserve the identities that we would expect to preserve. And allows us to define an outer product that is consistent with the inner product. So all of this makes it clear that the rho-calculus kind of matches the sort of linear algebra that you need to interpret quantum mechanics, with one exception. So far, at least my thinking that this far had not evolved to understanding the difference between setting up superpositions versus setting up entanglement. And there are two insights that I've had recently. So for the last several months, I've been kind of toying around. I'm going to skip this one. I've been toying around with what measurement means, and here we have we need to avail ourselves of some additional machinery. It's not particularly hard. It fits on a page, and it starts with a one-liner, right? So it begins with our notion of annihilation, right? So we say P annihilates Q if whenever you put P in parallel with Q, if there's, for all the R's that this evaluates to, R eventually goes to 0, right? So what we're saying is all paths out of P par Q go to 0, right? That's what this says. And we can relativize annihilation, right? So we don't have to get to 0. We could get to some R, right? We could say for all R prime, P par Q gets to R prime implies that R prime gets to 0. So all the paths from P par Q get to R. And so we'll write that this way, right? So this one we wrote this way, and then R annihilation is written this way. And you can see that if you put a 0 here instead of an arbitrary R, you'll get annihilation, right? That's clear. Yes?
Yes.
Okay, all right. So now pick all the R's such that we have R is, we have R annihilation of P and Q. Okay, so that's all of them. Then this thing is a set, right? And this thing is going to be a process, but it's only partially defined, right? So we'll take all the R's out of this set, and assuming that the set isn't 0. So when the set is 0, this is if there are no R's for which this happens, then we say that this operation is undefined. But if there are some R's, then we're going to take the sum of all of them, and I mean the process summation. So we're assuming a row with a summation. Does that make sense?
So instead of just one possibility for P and Q to only one path, we can basically have multiple paths.
Well, you could have multiple. You could have multiple paths here, but this is collecting all the ones, right? And notice that if you commit to one of them, right? If P and Q gets to one of the R's, right? You're persistently R, right? So this will go to one of the R's, right? And we have all the R's here, right? And once it's there, you get there forever, right? Yeah. Now, in fact, you can also argue, it seems to me, that if there is an R, it's unique. So let's see if we can prove that, right? Suppose you have 2 such R's, right? So I have an R and an R1 and an R2, right? So if I get to an R prime, then no matter what it is, right? I get to R1. So in particular, if I get to R2, from R2, I get to R1, right? And so, and symmetrically for R1 and R2, with their roles reversed. So R1 and R2 have to be the same. Do we agree?
Can you please repeat when you say R1, we can go from R2 to R1?
Yeah, so suppose I get to R2, right? Well, by definition, R1 also has this property, right? So I get to R2. Well, from R2 is just an instance of an R prime, so I can get from R2 to R1.
I see. So
Right.
both R2 and R1 and R2 are an instance of R prime.
Yes, since they're instances of R prime, we must get to, R1 and R2 must be the same.
I see.
Okay, so in point of fact, there's only ever one of these, right? Or none of them. Do we agree? Okay, all right, good. So now we can define another kind of multiplication. Right. So given a couple of names, right, then we can do the same sort of thing, right, which is just the name of whatever this is, assuming this is defined. And similarly here. And now this is different, right? Because what it's actually doing, so let's compare, right? So here we're just doing parallel composition, right? We're not running anything. We're putting two processes in place, and we're doing parallel composition, right? So there could be lots of reductions that are possible here, but we don't do them. We don't run them, right? So it could be constructing a red X, but we leave it static. Here, we are going ahead and running them. And that, I argue, is what's taking the role of measurement. Does that make sense?
I understand what you said, but I'm not sure that I can understand what you mean by role, how this makes the role of measurement.
In the sense that what constitutes our observables, or what's coming out of our observables, is going to be going to be changed forever, right? It's right. If we think about what a measurable is, right? When we make a measurement, we slide out of superposition. And that's really what's happening here. We're by running things to their completion, right? That's really what's going on here. We're running things until they can't go any farther. So there's
and
no.
This
Go ahead.
This running is who is doing the running? Is this by definition of?
It's the definition. It's the definition of this operator. There's no agent. It's just like if you apply this operator, then you know, it's like if you build terms using this operator, then that's the running.
I see. And this is different than using the first multiplication and apply eval, for example.
Well, you don't get an eval underneath a name.
But can we evaluate this name?
You could evaluate a name, but that's what that operator is doing, is evaluating names.
But you're saying this is not the same.
Right. Like when you run p par q, whatever's underneath a name is frozen. It doesn't move. Whatever's underneath an at, even if they're red X's, they don't move. They don't evaluate. So if you evaluate a row process, all the names are stuck unless you star them.
I mean, we can theoretically try to evaluate all of the names that we will find in the regex.
You can do, right? But that's not in the row calculus. You need a new operator. Yes?
I see.
Right?
And this is the role.
And that's what this operator is.
I see. So this is not just we have rewrite in the sense of putting something in par, and but not only that, with this operator we putting something together, and we will try to evaluate everything that we will find inside.
No, this only works on the names. It's not an evaluation of the process. This is an evaluation of the names in the namespace.
Okay.
So those two things are separate.
And is the reason for that because we already know how to evaluate processes?
Correct. Yes, we already know.
Oh, I see. Oh, now I see. In your definition, you're saying at par, at Q. Both of names. Oh, this is like a par for names.
No, it's not a par for names, right? That's what this is. Right. These two.
Okay.
Right. It's an eval for names.
Okay.
Okay. So that's that. And now I want to come to the other observation, which goes all the way back to the beginning. So I see that my thinking has been a little bit unclear because I was so fixated on this names as scalars thing. I missed something important. So scalars are not the same as observables. And that was something that I needed to distinguish in my mind. A scalar could be the result of making an observation, but it's not the same as an observable. And in the row calculus, the two roles are conflated, right? So when we make an observation, what we're really doing is we're going and checking what value is available at a given name, right? That's an observation in the row calculus. What value is available at a given name? And it turns out that what value is available at a given name is the code of a process. In other words, a name. So observables and scalars are the role of observable and the role of scalar is played by names in both cases. And so in order to complete the picture, we have to distinguish how it is that a name plays a role as an observable versus how it is when a name is a scalar. And it's clear, syntactically, right? A name is not an observable unless it's in one of two contexts, right? And that's something that we haven't kind of addressed. So I will just make some scratch paper down here and explain what I'm saying.
You said that name is not observable unless in some context.
Yes. It's not and observable. It's not. So again, when I talk about observable, I'm really talking about observables in the sense of quantum mechanics.
Can you just briefly say what is observable?
Yeah, so like momentum is observable. Position is an observable. Right. These are things that Heisenberg's notion is that those two things are not commutative. Those variables, when measured, are not commutative.
And is it observable when we measure and then we have the value and we are saying this is observable, or this is something that we don't know, we still didn't measure?
Oh, you're asked, an observable is something that can be measured.
Can be. Mm-hmm. It's not the value. It's something that can be measured.
Something that can be measured, right? So momentum is not a specific value for momentum. Momentum is the variable, the position that is played, the role that is played in physical systems that are constrained by certain laws of motion.
Mm-hmm, mm-hmm. Okay.
All right. So the reason this kind of escaped me is because, let's see if I can find, I'm just looking for, if you look at it, the notion of context is process context, right? That's a notion of context. But what we're really interested in is a different kind of context, right? So an observable, a name becomes observable if we have either this sort of context or we have this sort of context. And these contexts are different than our other contexts.
Oh, why there is a bang after?
Sorry, that was just
okay.
Word.
Mm-hmm.
That's weird. Let me see if I can redo this.
So this is what you meant by saying that name, that we cannot get the value on the name until the name is one of these two positions.
Yes. So this is a notion of an observable.
Mm-hmm.
Yeah, and those are different than names themselves, right? When I yeah, so that's so that's kind of the two insights that I've had to date is that I have to disambiguate observables from scalars. So we can do that. And I have to be able to talk about irreversibility. There is one other insight here. And that insight is that if you even in this definition here, we are getting non-locality, and I hadn't thought about that before, right? If we think of the free names as somehow giving us a notion of location, right? So in the pi calculus, you don't have a way to compare locations, right? It's just a big flat space, right? But once names have structure, then obviously you can compare locations. And so you can start to get, posets and other kinds of topologies. And so then names actually start to make sense as locations. And so an operation like this, which changes the free names, you do get non-local correlations. So, and in particular, you get non-local correlations when you do this, because you can potentially get names coming to the same how do I say this? These things could evaluate to the same thing. And because they evaluate, you're right, you'll get correlations throughout Q that you wouldn't otherwise see. So, so you will get correlations here, right? But you'll get potentially stronger correlations. Stronger is not quite the right word, but I think you see what I mean. So this, for a variety of x's, this may be the same thing. So Q may become more determined, more deterministic.
So even they are completely different structurally, and which means locations are different. They can be the same.
Yeah, they could result in the same evaluation. Yeah.
What this means? What kind of relation is that? I'm not sure that I understand when you say non-local correlation.
So Bell's inequality shows that you get states that are correlated, statistically correlated, even though they're separated in space.
I see.
Yeah,
I think I now have better understanding of quantum mechanics now that you are explaining this in this way.
Sure. Yeah, it's the same here. I feel like I really need to understand quantum mechanics because it's one of our most accurate scientific theories, right? Accurate out to 30 decimal places, and so it's really kind of a shining example of what you can do with the Western scientific techniques. And so it's probably a good idea to really understand it, especially since it's we will have quantum computing we will have serious quantum computing in the next few decades. So being able to program it means having a decent understanding. So I'm slowly inching up to all the different pieces. So we do get, we're able to provide models of everything that is there. And now what I have to do, so up to here, let's say, sorry, up to here, I have been able to verify the sorts of the sorts of identities one normally finds in quantum mechanics. Once I introduce this and this, I now need to go and verify some additional identities, and then I'm at the point where I can start to, model things like the Stern-Gerlach experiment, or the double slit experiment. And so then then we get much more interesting. Then things get more interesting, right? Because we can, within a very simple algebra, right? The rho-calculus fits on a page, and we have a couple pages more of definitions, and by comparison, I think its complexity is on par with, say, the ZX calculus, which is, it's sort of computationally complete, but it's certainly not all of quantum mechanics. So anyway, I think it has good complexity in terms of being able to present it to high school students. And therefore, we could potentially have another toolkit where we can go back and forth seamlessly between sort of classical concurrent computation and this quantum notion of concurrent computation. So that I think that would have some utility. Anyway, so that's kind of that's part of the point here. Now, the other point that I wanted to make very quickly. So that's one approach. Now, what we talked about. Let me go find it here.
May I just ask you about the scalars and observables? Now that you defined observables in this way, the names itself without this context, they are just the scalars.
Names are scalars, yes. Without those contexts, mm-hmm. there's no observable. Yeah.
Mm-hmm, mm-hmm. So when we are doing the measurement, we are using names, but we are basically going somewhere else to get the value. The value is not directly connected to the name.
Well, I mean, it's like, a position in a matrix or a position in a vector is not the same as the value in the vector, right? Mm-hmm. The position in the vector is the observable. The value is the thing that you see at the observable. So the position in the vector is the momentum. The value in the vector is what the value is measured of the momentum. Does that make sense?
Mm-hmm, mm-hmm. And now that we have multiple names and we are applying this new operator, we see correlation between these positions in some.
Correct, which is exactly like, seeing the correlation in these states. Yeah.
Okay, now this is something that I can imagine. Finally.
Yeah.
But here, don't we have one more level of indirection? I mean, basically, name is like a pointer to a value. I think it is where it is. But then there is the concept called momentum that may say this is where, or this is what the name represents. Isn't that, so aren't there like really three things? The one is a pointer to a value, and then the other is a description of what the pointer is about. So there's the pointer and the value and the description of the pointer.
Yeah, well, I agree with your ontology, but all of those things are present both in quantum mechanics and in rho. So in quantum mechanics, you didn't necessarily have to pick the second position in the vector to be the momentum. You could have decided that was position, right? So the position in the vector is the pointer to the value. The value in the at that position is the value, and how you assigned physical interpretations to the position in the vector is that's the physical interpretation, the concept as you're referring to it. And the same is true in the rho-calculus, right? So there's the context, right? The sort of the position in the vector. There's the actual value at the name, and then there's the physical interpretation. So all of those are present. So let's see. Hang on. All right. So let me go here. So I had to recover. Joe did some destructive modifications on my original paper, Joe Dinman. And so I had to go back and recover it. So this was the original paper. And so what I want to do is to, So the idea is that you can take any rho-calculus process and you can put it in a context like this, where you have a parameter n, which is how much phlogiston you provide. And then you have 3 channels, the faucet channel, whatever the phlogiston value is, and then a step channel, and it's going to be defined to be you provide that much phlogiston, and then you wait at the faucet for some phlogiston, and you provide a fresh return channel, and then you send along the step channel the phlogiston and the return, and on the return channel you wait for the thing to run, and then you run it. And so now you can define rho-calculus, a transformation on the rho-calculus like this, right? So 0 with the step is just 0. A for comprehension with the step will wait from the step for the return channel and the phlogiston, and send the for comprehension which you've translated the continuation with the step. Right. And so what this does is, if you run through all of these, you'll see that this gives you we won't ever do any computation without paying for the steps. Right? Every IO event will result in having to pay some phlogiston, and then you can show that if you have enough n, right? If you always have enough n, so enough phlogiston, then the metered version of the program is the same as the program without metering. Because any step you can take here, you can take here, and any step you can take here, you can take here. And that's something, for example, that Ethereum never proved. It may seem obvious, but it's not necessarily obvious. There are all kinds of dragons in that sort of complexity. So it's a good idea to have. It's a good idea to have, to have a formal arrangement so you can prove that sort of thing. So you can see how simple this is. So the nice thing is that this also gives you sort of the basic framework to talk about both debugging and reversibility. And so what I'd like to suggest is that for those who are interested, take these basic definitions and modify them to produce a debugger, and modify them to do reversible computation. And it's obvious what you need to do, right? You need, like, whenever you do a for comprehension, you have to record both the value that you got and the fact that you were going to do a for comprehension.
So
and
instead of,
Go ahead.
sorry, I'm just thinking, instead of right now what we are doing with cost accounting, we basically just storing the chain of numbers.
Correct.
But for the debugging, we basically need to store the rolling terms.
Correct. That's exactly right. Yeah. And you have to do it on both sides of the IO, right? So here, you have to, before you take the IO step, you have to record that you were going to do this and what the value was, right? And that allows you to, and once you have reversibility, then you can go back to this this other thing that I was doing and do the where I was encoding the symmetric monoidal category constructions, and you can implement cup and cap. So next week, if you come with definitions of reversibility, which should be very straightforward, we can plug them in and provide definitions of cup and cap. All right. Thanks everyone for your time and attention. I'll see folks at the developer stand-up.
Thank you. Bye-bye.